Hey everybody, Justin Miller, College Physics here. We are going to be looking at an LC circuit. So let's just go ahead and describe what that is first, and then we can proceed to see what is to be seen. All right, so what we're going to do is we're going to take a fully charged capacitor and connect it with an inductor of some inductance L. We'll put a little switch here so that the switch is open right now. And let's not put that in. That's unnecessary. All right, so we got the switch, we got a fully charged capacitor, we got an inductor, and what we want to do is think about what's going to happen with this when we close the switch. So we close the switch. What do we got? Well, we've got a completed circuit. We've got a pathway for this buildup of electrons on this plate to go ahead and try to negate the abundance of protons over there, or the deficit of electrons. So that's exactly what's going to happen when we close the switch. We're going to get a current, right? Because we'll get electrons moving. But as we have this current, we're also going to get something in the inductor. Once the current begins, what happens? There's a change in magnetic field flux through this inductor, which produces or induces an EMF due to the inductance itself, which is kind of like, again, a back EMF. Self-induced EMF, which ultimately is going to store some energy in this inductor. And well, what's going to happen then? Well, there's energy stored in this capacitor. It gets released in the form of the current. The current going through in the inductor ultimately stores energy in the inductor in its magnetic field. And then, well, what happens? Once we have all the charges left, we have a maximum current going through the inductor, and then, well, that current starts to drop to zero, right? What happens when it's dropping to zero? Well, we got another change in magnetic field flux then. We got a reduction in the magnetic field and a reduction in the flux then. And what happens? Well, the inductor starts to release its energy that it's stored, which further transports electrons onto this plate. Until when? Until all the electrons that were separated onto this plate are now separated over here. And all the energy that was stored in the inductor is gone. No more magnetic field, no more change in flux, fully charged capacitor. But assuming that we don't open the switch right then, what do we have? Well, the capacitor is fully charged, now it can discharge. Starts to discharge, we got current going the other way, or the electron current going the other way. Magnetic field flux change in, self-induced EMF, and stored energy, released energy, stored energy, released energy. So this is a system in which we really just have this continual exchange of energy stored by the capacitor, then energy stored by the inductor, and intermittently by both of them. But what we're going to do is we're going to make a couple assumptions here, and number one is we're going to say that there's no resistance, zero resistance. We don't want to add a resistance into this. This is more of an idealization here. Just want to see what we get out of it. No resistance. And it's an isolated system. No energy loss, basically, is what we want to treat this as. Say, no energy is lost. We've either got energy stored in the capacitor and or energy stored in the inductor. And that's basically that. So, if this is an isolated system, change in energy must be equal to zero. That's, again, the total. Well, what is the total energy? The total energy is the sum of the energy stored in the capacitor and the energy stored in the inductor, which we could call U sub C plus U sub L. U sub C is energy stored by the capacitor, which we know we can write in a few different ways. We have that U sub C, we're going to write it as Q squared over 2C. That's a nice way to write the energy stored. Q is the charge stored, C is the capacitance of the capacitor, and U sub L is the energy stored by the inductor. The energy stored by the inductor is 1/2 Li squared. 1/2 multiplied by the inductance multiplied by the current going through the inductor squared. Now what's going to be changing is the charge stored by the capacitor is going to be changing with respect to time, and the current through the inductor is going to be changing with respect to time. Sometimes we'll have that the charge stored by the capacitor is a Qmax, at which time there is no current. Sometimes we'll have that there is no charge stored, at which time we'll have the maximum current. And sometimes we'll have some charges stored and there's some current. So ultimately, Q and I here are both functions of time. They are time dependent. So the energy stored are time dependent. But if the total change in energy is 0, because this is a conservative system, we must have that dE by dt is equal to 0, which means that du sub c dt plus du sub L dt is equal to 0. That's it. Total change in energy is equal to 0. So this is what we want to focus our attention on to see if we can extract out the time dependences of the current and the charge accumulation. Or if we could just do something with it. And that's what we're going to do. Something. All right, so what can we do with this? Well, again, we know what U sub C and U sub L are, so we'll focus our attention on this portion right there, and it being equal to 0. So what do we have? We've got that d by dt of q squared over 2c plus d by dt of 1/2 Li squared is equal to 0. So what do we need to do? We take some time derivatives. We note again that q and I are functions of time. So we're going to take the derivative of those. Well, the 1 over 2c just comes out, and the L over 2 comes out as well. And then we've got d by dt of q squared. What is that going to be equal to? Well, we've got this. We've got 1 over 2c times d by dt of q squared plus L over 2 times d by dt of I squared is equal to 0. So I really just want to focus on these particular portions right here. The time derivative of q squared, where q is a function of time itself, is going to be 2q dq dt. That's it. So let's go ahead and write that. And we've got the time derivative of I squared is going to be 2I di dt. Sounds good enough, right? So we've got that this is then equal to 1 over 2c times 2q dq dt plus L over 2 times, let's put that in, times 2I di dt is equal to a 0. So we could clean this up a little bit. You see some factors of 2 cancel out. That's fine. But what we have here is something that we can start to play around with a little bit more. So I'm going to take this. We're going to come up over here and see what we can do with it. So we got some relations between Q and I, right? I by definition is dq dt. That's right. That's how we define current, right? The time rate of change of charge. So with this, we can start to rewrite some stuff out, right? So we've got I is equal to dq dt. That means that di dt is d squared q dt squared. So let us rewrite some of this stuff out. And get rid of these factors of 2. Those cancel each other out. And we've then got ourselves that 1 over c times q times dq dt. Let's just keep that as dq dt right now. Plus L times I. Oops. Sorry. I'm missing the dq dt. Let's leave that. We are going to leave that. dq by dt plus L times I. Well, I is dq by dt, so I'm going to put that in. dq by dt. And we've got di dt. Well, that's dq squared dt squared. d squared q, sorry. d squared q dt squared. All has to be equal to a 0. Let's just go ahead and put a little parentheses around that. So what can we do with this? Well, we notice that there is a common factor of a dq dt right here, dq dt, dq dt. We can factor that out and divide 0 by it, and that just goes away. So this factor here can vanish, and we are left with this. 1 over c times q plus L d squared q dt squared is equal to 0. What can we do with this? Well, let's get everything except this over to the other side. So we've got a nice little expression here. So if I put everything but this over to the other side, I'll subtract this from both sides and then divide by L, and we will have ourselves that d squared q dt squared is equal to negative 1 over LC times Q. That is a nice expression right there. Really nice expression, because we could solve that out. This expression says that there is some function Q, that's a function of time, that we could take 2 time derivatives of it, and we could get that same function back, and in addition to that, the negative of some constant, which happens to be negative 1 over LC. So, think of any functions that if you take 2 derivatives of that function, you get negative that same function back. We'll deal with the constant there momentarily. So you start thinking about some things. I want a negative after taking 2 derivatives of it. Well, negative of the same function. Hey, what about sine or cosine? Those seem like functions that, yeah, I take 2 derivatives of cosine, and I got a negative cosine. Take 2 derivatives of sine, I got a negative sine. So that's a good start right there. Then we got this constant factor, this 1 over LC that we've got to deal with a little bit. Well, how are we going to get some constants? So let's think about this. We're taking 2 derivatives of some sinusoidal function, sine or cosine, and we're going to get 2 factors of some constant then that should become this 1 over LC. So let us do this. Let us call this 1 over LC omega squared. So let 1 over LC be equal to omega squared, such that we'll get a factor of omega each time we take the derivative of either the sine or the cosine. So that we get 2 factors of it, we'll get an omega squared, and that'll be equivalent to 1 divided by LC. So what we have with this then is that d squared q dt squared is equal to negative omega squared times q. Where again, q is some function of time that describes the charge, right? The charge on the place of the capacitor as a function of time. So, we reparameterize stuff a little bit. Let us go ahead and put this up here because we've got a little bit more to do. Put this on down, and we want to deal with this. What kind of equation is this? That's right, this is a differential equation. We've seen differential equations before? Of course we have. Have we seen any differential equations that look a little bit like this? And the answer is probably with an oscillating mass spring system. Simple harmonic oscillator was very much like that form. But if we haven't seen it or we don't remember, that's okay too. The main thing is that there is a solution for this. we want to get what Q of t is. It solves that expression out. Now we find Q of t satisfies the expression. Ooh, squeezing that in. What expression? This expression. So again, we said something sinusoidal. Let's pick cosine, and then we'll deal with the ramifications of that afterwards and see if that was a good pick. So let us say Q of t is equal to some constant a times the cosine of, well, we don't just want to say theta, it's going to be cosine of some function with time in it. So there has to be some time variance in there. And again, if we're going to be getting 2 factors of omega by taking 2 derivatives of that, hey, let's just put that be an omega t. That sounds like a good idea, right? So let's call this omega t, and then we'll put a little phase factor on here, phase constant, that'll just allow us to manipulate things if necessary. So let us say that Q of t is equal to this, a cosine omega t plus phi. Let's see if this actually satisfies this equation. Let me say, how did you come up with that? A little bit of intuition, a little bit of experience, and yeah, I've done it before. But nonetheless, this is how we start thinking about solving these differential equations and such. Nonetheless, what happens if we take 2 derivatives of this? Well, let's look. D squared by dt squared of a times the cosine of omega t plus phi. What's that going to be equal to? Well, that's going to be equal to 1 derivative of, well, let's take the derivative of this. Derivative of this is going to be equal to, derivative of cosine is a negative sign. So we'll have a negative a times the sine of omega t plus phi, and then we got this interior portion right here. We take the derivative of omega t, and that just gives us omega. So we get this, negative a omega sine of omega t plus phi. So there's 1 derivative. We take 1 more, and we'll see what we get out of this. So this then is going to be equal to, well, this is just a constant right here, a omega, there's a negative sign. We take the derivative of sine of omega t plus phi. Derivative of sine is cosine, and then we got that omega t. We'll get another factor of omega, and we get ourselves negative a omega squared cosine of omega t plus phi. So there's what happens when we take 2 derivatives of what we're saying is Q of t. What do we get? Well, let's write it like this. This is equal to negative omega squared multiplied by a times the cosine of omega t plus phi. This is what we said was Q of t. So what do we get? We get this. We get negative omega squared times Q. That's exactly what we said we need to satisfy. That expression satisfies it. So this is a general solution for the system in terms of solving for Q of t. This right here. Of course, we've got to make some sense of some other things regarding it, but this, again, is the general system. And furthermore, we have that omega squared is 1 over LC. So omega is 1 over the square root of LC. And omega is in this cosine function there. What does that really do for us? Well, let's look at a couple things regarding this and move forward. So again, this is Q of t, the charge accumulation on the plates of the capacitor as a function of time. Let us deal with this little phase constant, that phi right there, in the expression. Phi, ultimately we just want to say, what is phi going to be? Phi is going to be something that really depends on our initial condition of the system. Initially, we're saying fully charged. Initially, Q of t equals 0 is equal to Qmax. So this is going to tell us a couple things, because now we've got ourselves that Q of t equals 0 is equal to A times the cosine of 0 plus phi. So what's the cosine of 0 plus phi? Well, we know that the cosine of 0 is 1, which would just give us A. If we put in anything else except 0 here, or factors of 2 pi, then we're not going to get just A. We're going to get something else. What does A really represent? Or is that represents the maximum value that Q can have. Because again, something that's sinusoidal just goes between 1 and -1, 1 and -1. The amplitude really gives us what the maximum value is, either positive or negative. So we get a couple things out of this. Number one, A is equal to Qmax. So now we can have this, Q of t equals 0 is equal to Qmax times the cosine of phi. We don't need the 0 there anymore. And then we just ask ourselves, well, if we're saying that at t equals 0, we have to have Qmax, then phi has to be equal to 0 if we chose cosine. So that Q of t equals 0 is equal to Qmax. Check. That's what we wanted. So we could have picked sine to say that that was Q of t, but in that particular case, if we pick sine, we would have A times the sine of 0 plus phi has to be equal to Qmax, which would mean that this phi has to be pi over 2, or negative 3 pi over 2. 3 pi over 2, excuse me. So then we got a phase constant. We won't really deal with phase constants much in this particular course, so next semester we will. But for now, just kind of accept that this just allows us to pick a certain state that we begin in, or it correlates with a certain initial state. So what do we get out of all this? We've got Q of t is equal to Qmax times the cosine of omega t, where omega is equal to 1 over the square root of LC. All right, so we've got ourselves the variation of Q with respect to time. What can we do with that? Well, we can get ourselves the variation of the current with respect to time, because we know that I of t is equal to dq of t dt. So we take the time derivative of this. What are we going to get? We're going to get ourselves a negative omega Qmax times the sine of omega t. Negative Q max omega times the sine of omega t. Well, what is this? This has to be the current as a function of time. Current as a function of time follows this. And what do we have? We have to have that I max is equal to Qmax times omega, which is equal to Qmax over over the square root of LC, which is the max current. So we can write this out as I of t is equal to negative I max times the sine of omega t, where I max is Qmax times omega, or Qmax over the square root of LC. I max is Qmax over root LC. Very nice, very nice. Why is that nice? Because we know the variation of both the current and the charge accumulation on the plates of the capacitor as functions of time in the circuit, and it's completely sinusoidal. What do we have? Well, the charge on the plates of the capacitor starts out as a max, goes to 0, then has a reverse polarization, goes to its maximum value in the opposite polarization, then proceeds to go to 0. Let's just draw out. Let's begin. cement, in a sense. So we've got Q of t. Let's not put that so far down. And t. What does this look like? Well, again, this is cosine. This is Q max. This is negative Q max. That's 0. We start out with the maximum charge. The charge starts to come off the plates. Once we close the switch at t equals 0, eventually there's no charge on the plates. And then as time continues on, charge accumulation builds up in the opposite polarization until again we have the maximum amount of charge. And then it starts to discharge again, goes down to 0, and then is back in this same exact positioning, orientation, or portion of the system. Back to where it started. And then what does it do? It repeats. And what does it do? It repeats again, and again, and again, and again. We just get something that is continuously discharge, charge, discharge, charge, discharge, charge. So that's the current, the charge accumulation is a function of time. If we look at the current through the inductor as a function of time, try to match this up. This one's a little bit harder to sync up for me. So we'll do this. I gotta put little cheater marks so I can match this up as best I can. So ultimately what we should get is when the charge is a maximum amount accumulated on the plates of the capacitor, we should have ourselves 0 current, 0, 0. And then when we have no charge, that's when we have the maximum current. No charge, maximum current. No charge, maximum current. So sinusoidal, this should be negative. I messed these ones up. This one's up here. This one is down here. This, it's negative sign, and we've got this. Something of that nature. This didn't quite go up as far as I wanted, but connecting the dots is harder than it seems sometimes, for me at least. That is a fault of my own, but nonetheless, hopefully you can kind of see what's going on here. What is that negative sign? The negative sign is just directional. That's all that the negative sign really does in terms of this is when the electron current's going this way, and this is when the electron current's going the other way. That's it. Negative, positive, negative, positive. But what do we get here? Again, we get this sinusoidal behavior for the current. And its alternation is just shifted over by pi over 2 radians with respect to this. 3 pi over 2 radians. At any rate, this is what we get. So there's one other thing that we want to look at for this, and that is the actual oscillatory rate. So let us do that. So because this is oscillatory, just doing the same thing over and over, we can start to look at the cyclic behavior of this. So let us do just that and kind of key in on something here. So we'll look back at this Q of t. Again, I'll write it again. Q of t is equal to Q max times the cosine of omega t. So there's our function that describes Q of t. Great. What can we do with this? We know that it repeats. Repeats every 2 pi radians, right? So from t equals 0 to t equals 0, omega t is equal to 0 to omega t equals 2 pi is one cycle of the oscillation. So what does one cycle look like? It looks just like this. We start in this state, maximum charge, discharges, then begins to charge opposite polarization, then discharges, then begins to charge in the initial polarization, and we're back right here. This right here is one full cycle of the oscillation that will continue. One cycle. Going from omega t is equal to 0 to omega t equals 2 pi. If omega t is equal to 2 pi, cosine of 2 pi is just 1, we got Q max back. So this is what we want to look at. So with this, we can now do something. Let T, capital T, be the period of the oscillation. Period is the time it takes to complete one full cycle. By definition. So we got this capital T, let's just stick it in here, because after omega t is equal to 2 pi, we've got ourselves one full cycle has elapsed. So we have that omega times capital T is equal to 2 pi. Every 2 pi radians, we repeat back to where we started. So that gives us the period T being equal to 2 pi divided by omega. Well, that's for anything that's sinusoidally varying in a cyclic manner that we can make this sort of correlation here. But the nice thing with this is we know what omega is. Omega is physically 1 divided by the square root of LC. It depends on the capacitance and the inductance in the circuit. So with omega being equal to 1 over the square root of LC, we've got that the period, the physical time it takes for one full cycle to be completed is going to be equal to 2 pi root LC. And that will be some number of seconds or milliseconds or some amount of time, we'll just say. There it is. There's the time it takes for one full cycle to complete itself. And this is what we were really after. We're after both, again, the sinusoidal behavior of the current and the charge accumulation, and we're able to extract out what the actual time correlation with one full cycle is. Consequently, omega is generally called the angular frequency. It has units of radians per second. It's much like angular velocity. If you look at the correlation, we will at some point look at the correlation between angular velocity, uniform circular motion, and sinusoidal motion. So every 2 pi radians that goes by, ultimately, you've got a repetition. That's correlated with omega itself, the angular frequency. Frequency in cycles per second is called hertz, Hz, and we have that F is equal to 1 divided by T, which is omega over 2 pi. And this is in general. This is frequency in hertz. Which is a lot of times easier to discuss because it's cycles per second. We just call it hertz. So 60 hertz, 60 cycles per second. Talking about things in terms of angular frequencies, radians per second, isn't super intuitive in getting an understanding of how quickly things are occurring on the cyclic, in a cyclic manner. This is what we've got for these LC circuits. We can find some other quantities that we'll be using quite a bit as we do AC, and that's what we got, right? We've got an alternating current here. So that's another key aspect of this. This naturally produces AC, an alternating current. Goes one way, goes the other way, goes one way, goes the other way. And there's the frequency of the alternation in the current. F, which is omega over 2 pi, which is then the inverse of this, 1 divided by the quantity of 2 pi times the square root of LC, quantity closed. All dependent on the inductance and the capacitance. That's what it all comes down to. All right, hope that was fun for you. It's fun for me. I'm a little hot, but that's okay. Until next time, be well.